Making things go fast is one of the priorities in many industries using C++. Monte-Carlo simulations are one of those things across every single industry, especially finance. But how can we use the CPU at its fullest capacity? Let's take a look at a simple Monte-Carlo simulation and how we can use multithreaded to speed it up. And at the end of this video, I'll share a little trick with you to make it even faster. First of all, let's define our little toy Monte-Carlo example. We'll toss a coin and bet it will land heads, so every time it does, we'll earn $1. And every time we get tails, we'll lose it. We want to find the expected value of this bet per toss. So we'll toss the coin many times, divide that by the number of times, and see what happens. By the law of large numbers, the more times we do the experiment, the closer it will get to its real expected value. This is fairly straightforward to do in C++. We can define this simple coin toss method, which just returns -1 or 1, with the same probability, and then the simulation method is as follows. We need a random number generator to feed the coin toss function, and we need a place to store the results, so I'll use an array. By the way, an array needs to know its size at compile time, so I took the number of simulation and passed it as a template parameter, but you could just use a vector and pass it as a function argument as well. It doesn't really make that much of a difference. And then for every simulation, we'll toss the coin the number of times we've decided. Once every simulation is finished, we just sum up the result and divide it by the number of simulations to get the average. Pretty simple, right? Well, there's a little problem. I've defined in the main function 100,000 simulations with 10,000 coin tosses per simulation. Guess how long that takes? Surely we can do better than that, can't we? Thing is, we don't really care if one thing happens before the other. The order of execution won't really change a thing. The result will still be the same, so we should do as many things at the same time as we can. In order to do that, we need to know how many threads we have, and the STL gives us that functionality. And then we should know how many tasks every thread should perform. Having that defined, we'll need to store every thread we execute to be able to join them after they're done. So we'll create a vector for that. And then we'll just make all of these tasks do their jobs. Little parenthesis here. Threads take functions as an argument. So we could write the function in one place, then create the thread with that function, and then move it to the vector, or we could just do it like this. We construct a function as a lambda with ImplaceBack. Why is it good? Well, ImplaceBack passes whatever we throw at it as a parameter to the constructor of the object we're building. Since we're building threads, we are essentially calling the constructor in place with the lambda as argument, so we don't need to copy or move it. It's getting built where it needs to. Now for the lambda itself, we need to generate random numbers in here. And for that, we'll need to create the random number generator for every thread. This is because it's not thread safe, so if we passed it from the outside of the thread, we could get concurrent access problems. In the loop, we need to know what thread we're in and execute the appropriate tasks. The logic to know what we need to execute is a bit tricky at first. We know how many tasks we should perform in each thread. We calculated that before. We also know what thread we're in. This is a parameter to our function. So we should multiply the thread number by the number of tasks per thread and go from that index to the end of the number of tasks per thread. And then we just perform the simulation and store it in the array. Note that we don't have concurrency problems while accessing the array, because every array index is only ever accessed by one thread. But if this was not the case, we would need some sort of synchronization mechanism for handling all the threads trying to access the same buffer. Once all this is done, we have to wait for all the threads to finish their jobs and get synchronized. But check this out, there still might be some work left to do. If the number of simulations could not be divided by exactly the number of threads, there are some simulations left. So we'll take that case into account. Finally, we need to accumulate all of the results and return them divided by the number of simulations. Checking the time now is significantly faster. That is an impressive speed up. At the beginning of this video, I promised you a little trick to make this even faster. Right now we have our 6 times its speed increase. Well, that makes sense, my CPU has 6 physical cores. But we can do the following. Instead of spawning as many cores as I have, I can spawn more, even twice as many, and get a significant speed up. This technique is called oversubscription, and I highly encourage you to take a look at it if you're going to work with multithreading. With these settings, we can run the program again and check it out. Quite a difference there. Hope you learned something in this video and enjoyed the explanation, but for now, I'll see you in the next one.